Very well. For many important reasons in structural mechanics, we need to be able to compute the moment of inertia of an area. Typically, that area represents the cross-section of a structural member, like a beam, a column, etc. And so we're going to go through some examples of how to compute the moment of inertia of different types of cross-sections. So the easiest one, the first one, usually we encounter is a rectangular cross-section of width b and height h. And we want to compute that moment of inertia with respect to the center of gravity, or the centroid of the cross-section, which in this case is at h over 2. And let's say here we want to compute the moment of inertia with respect to the x-axis. So in this case, this would correspond to a beam coming out of the board like this, subject to bending this way. Like that. So how do we compute that? The general formula is the integral of y squared dA over the whole area. And the challenge here is to define this dA element. We're going to say, for this example, there are several ways of doing this, but let's say, for the sake of this problem here, that we are going to say that this cross-section is the sum of infinite number of infinitesimal slices like this, horizontal slices. Each one of these slices has a thickness equal to dy and a width equal to b. Clearly, if we integrate b dy along y, we will get the total area, and that's easy to verify. B dy from minus h over 2 to h over 2. This is 0 here, and the whole height is h, and we have positive h over 2, negative h over 2. So this becomes b times y evaluated here, which gives you b times h, which is the area. So this is a valid way to formulate a dA, because if you integrate it, you get a. And so in this case, the moment of inertia would be the integral of y squared times dA. And in this case, our dA, as we said, is b dy. And that integral, because it's formulated in terms of y, goes from minus h over 2 to plus h over 2. B is a constant, goes out. Basically, we have b times the integral of this which gives you 1/3 b y cubed from minus h over 2 to h over 2. Now we just have to substitute in. We have 1/3 b h over 2 cubed minus 1/3 b minus h over 2 cubed, which results in 1/3 b h cubed divided by 8 plus the two minuses, right? And it's cubed, so the minus doesn't disappear. 1/3 b h cubed over 8. And that gives us 1/3. 3 times 8 is 24, but there are two of those terms, so it's 1/12 b h cubed. And that is the well-known result for the moment of inertia of a rectangular cross-section around the horizontal axis that goes through the center of gravity. If you wanted to calculate the moment of inertia about the vertical axis, y, basically the only thing you have to do is switch b and h. And so, in summary, you have inertia around x, 1/12 b h cubed, inertia around y, 1/12 h b cubed. As you can see, if you have a cross section that is kind of tall like that, then the moment of inertia around that axis is going to be significantly higher than the moment of inertia around the vertical axis. So suppose this height here was 3 and this one was 1, this width, you basically are going to have something here that's going to be 9 times the inertia of this one. So if you have to resist loads that are being applied on the beam like this, which create bending around this axis, you are much better off using the beam in the vertical direction as opposed to using the beam like this in the horizontal direction. So this is the best option. This one is not, because this has a much lower moment of inertia, which, as we said before, because of the formula for bending stresses, you're going to have a lot larger stresses here as opposed to here. So here the stresses are going to be low, here the stresses are going to be very high. So this is the right way to place a beam when subjected to transverse loads that are in this direction. So the general rule is you want to place the beam with the dimension that is larger aligned with the direction of the load.